So, good morning, everyone. My name is Akinlele Kondane, popularly addressed as Global Pythagoras. The main purpose of doing this global maths groupings broadcast is just to spread the language of mathematics around the world to let people know that math is beyond X and Y. So today episode with my guest is here for us, is fully prepared for us. So from Cyprus. So the topic for today is math is the blueprint of the modern world and innovation. So I would like our speaker to introduce himself for us to let people know that we are available for this program. Kindly introduce yourself.
Sure, thank you, Akinley. Um, my name's Jerry Doherty. I've spent over 40 years in international education, teaching and then teaching mathematics, and then leading schools across the world, including spells as regional head of education for Southeast Asia and time as principal and headmaster of various international schools. And what's been the constant along the way for me is a conviction that education has to be learner-centred. It should be built around curiosity and agency and not compliance. And maths is sort of where that conviction gets tested the hardest, I think, because it's the subject that students are most likely to decide that they're just not good at. So my route into AI really came from that problem. I wasn't chasing the technology for its own sake. I was looking for a rich way to design inquiry-led learning at scale, at a scale that one person couldn't manage alone. And so that's where it's brought me today.
Yeah, thank you for telling us that. So the first question we have here is, can you tell us about your journey into mathematics education and AI?
Yeah, well, as I said, my journey into mathematics education has been a long one. It started in 1982 when I started teaching mathematics, and then went on to teach mathematics in the UK and in several schools in something like 13, 14 different countries across the world. The introduction into AI in terms of mathematics has really come from the work that I did in my master's degree dissertation study, and that started. I did that in the years 2000, 2001, where I was inspired by the story behind the human story, behind the development of Fermat's last theorem, which is the story, an amazing story of a problem in mathematics that lasted over 350 years, and all the greatest mathematicians of the time tried it but couldn't solve it until eventually an English mathematician working at Princeton at the time, a gentleman called Andrew Wiles, eventually did manage to solve it. And even then, his story in itself is quite an amazing thing. And so the story behind it is the human development of all those people who tried and who ultimately contributed to the final proof of the theorem. But I taught a course, or created a course, on the history of mathematics for my students, and I was teaching in a school in Athens in Greece at the time. And I wanted to test their opinions about the nature of maths, their understanding of the nature of mathematics, and their attitudes towards it. So I created this course and a little booklet around the idea of Fermat's last theorem and the characters and the mathematicians involved in the story. And then at the end of each sort of little chapter, there were some activities based on the mathematics that of the mathematicians that they were learning about within the story. And I'd always wanted to make a digital version of that. And understanding that, you know, the skills involved in creating something like that would take quite a significant amount of time to learn. Whereas nowadays, with the advent of AI, all of that becomes possible. And that's what's brought me into it, really, is to, I've always wanted to create that digital version. And now I more or less have.
Thank you for that. Thank you for that. Thank you. So the second question we have for you today, how has been international education can students shape your view of mathematics? Can you hear me my question?
Sorry, could you repeat that, please? Could you repeat what you asked me there, please?
How has been an international education can students shape your view of mathematics?
I would, well, I'm not sure that being an international education consultant particularly has shaped my view of mathematics. But having been an international educator for 40 plus years certainly has shaped my view of mathematics. And I suppose working across those very different countries and systems teaches you something which is humbling, really. That maths itself is universal, but the way we teach it absolutely is not. The same idea, a theorem, a proof, can feel like an arbitrary rule a student must obey in one classroom, and yet a genuine discovery a student gets to make in another. The maths hasn't changed, but the framing has. And, you know, in many countries across the world, it's almost something that some students say with pride, is that, oh, I was never any good at maths. And yet, if you go to countries like Greece or China, for example, the Greeks are very proud of their mathematical legacy. And so, you know, they feel it's something to be really proud of, to be good at maths. Whereas in some countries, it's almost the opposite. They're quite proud of the fact that they're not. So it's interesting working across different countries and different cultures. The maths is the same, maths is maths, but people's attitudes towards it can be quite different.
So what you tell us that math is beyond what people think. It's beyond solving for X, Y. That's great. Thank you for that. So the next question we have for you today, why do you think math is the blueprint of this modern world?
Well, every piece of technology that you touch is mathematics made physical.
Yeah.
The codes that let you let your phone connect, the linear algebra behind every image on a screen, the calculus inside weather forecasts and engine design, and the number theory securing every payment that you make online. Blueprint is exactly the right word, because a blueprint isn't in the building, but nothing gets built without one. And so maths is the layer beneath the layer, really. It's invisible precisely because it works. And the irony is that people who depend on it most are the ones who were taught to fear it often.
Thank you for that. So math is the blueprint of the modern world. That's great. So the fourth question we have: how does the history of mathematics influence the modern in technology and artificial intelligence nowadays?
Well, this is quite close to my heart because I make short animated movies exactly about this. The thread I keep finding is that today's breakthroughs sit on foundations that were laid centuries ago. The Boolean algebra, for example, behind every computer chip comes from the 1850s. Bayes' theorem, which underpins a great deal of modern machine learning, is from the 1700s. The matrix methods inside today's neural networks were worked out long before there was even a computer to run them. If you think about Leonhard Euler's network theory, that's the foundations of all modern networks, whether it be the internet or phone or communication networks. Without that, I wouldn't be sitting here talking to you today. So, all of this goes back centuries, and very often the mathematics that was being developed then, we didn't realise how important it was going to be centuries later. And in some cases, these things were problems for their own sake and didn't seem to have any relevance to something or any application to something. Number theory is a classic example, and the story of Fermat's last theorem is a classic example. Because when Andrew Wiles did manage to prove it, he was building on all the wonderful contributions that people had been making since the 1500s. And ultimately, there's a strong component, the idea of elliptical curves and modular forms underpins much of what we now know as cryptography, which is the foundations, of course, of our secure communications for the banking world. So the history of mathematics has a massive role to play in the development of modern technology and AI.
So what you are telling us now is that math is the foundation of AI and the modern world.
Absolutely. And any technology.
Yeah. Thank you for that. So the next question we have for you is that, can you share an example of math driving AI innovation?
AI innovation. Well, yeah, as I mentioned to you, that mathematics almost took pride in its, in some cases, in its uselessness, the idea of number theory. But then in the 20th century, it became the backbone of cryptography, the thing that makes secure communication, online banking, and e-commerce. This useless subject turned out to be holding up the entire digital economy. And so the lesson I draw is that you genuinely cannot predict which idea will matter, which is the strongest argument I know for protecting curiosity-driven learning and not reducing everything to its immediate utility.
Yeah, thank you. So, me too. I heard about the cryptography when I was in London level here in FUTA. So they tell us that math is the one of the backbone of cryptography. So that I think that's great for driving AI innovation. So the next question we have for you here is, how does professional development help education using mathematics better?
Sure. Good professional development does something quite subtle. It shifts a teacher from delivering procedures to orchestrating inquiry. And that's genuinely hard, because most of us, certainly from my generation, were taught procedurally ourselves. So we have to almost unlearn a stance before we can teach a new one. And so the biggest shift comes when a teacher rediscovers the why behind what they teach, so that when a student asks, but why does this actually work, the teacher can meet it with curiosity instead of changing the subject. In my own professional development work, whether it's on digital transformation, AI or pedagogy, the technology is never the point. It's downstream of that change in stance. A teacher who's recovered their own curiosity will use any tool, any technology well. So yes, professional development is vitally important in changing the way that we approach the teaching of mathematics to something which is inquiry-led and will spark or reignite the curiosity that naturally exists in young people.
Yeah, thank you for that. Thank you. So let's move to the next question so we can quickly do everything fast. So the next question we have here is, how can students see mathematics relevant in real life? How can students...
I think we've touched a lot on some of that already, but I think the mistake that we often make is trying to bolt the relevance on at the end. And, for example, when here's, where you might use this someday, but by then you've lost them. Relevance has to be the starting point. In the curriculum work that I do, every lesson opens with a driving question. A real genuine question that maths actually answers. And so the students get a chance to feel the relevance before anyone names a single technique. Kids don't disengage because maths is hard. They disengage when it arrives as a solution to a problem they were never shown the existence of in the first place. And so if we can flip that order, and a lot of the so-called motivation problem just simply disappears. It's all about sparking curiosity, rather than, it's got to be built in and not bolt on, essentially.
Yeah, thank you for that. So math is relevant in what we are doing in the model world or what we are doing because math is working behind everything we are doing nowadays, right?
Uh, Absolutely, absolutely.
Yeah, thank you for that. So the next question we have here is how can AI and mathematics make learning more exciting?
Well, it it lets us build learning that responds. Um, for again, for example, with the short animated movies that I create about famous mathematicians throughout history. Um, I've also created immersive virtual reality maths museums and maths escape rooms, um, where the children can step inside the worlds themselves and um, tackle these problems that famous mathematicians were working on, and which then allows them to put in the password to the next stage of the journey. So all of this has become possible in the last 2 or 3 years. I could never have created anything like that. Even the movies that I create, that would have required a whole studio and a multi-million-dollar budget, and now you can create them for in a relatively short period of time on your own, and for not anything like $1 million. And that's all been possible because of the advent of artificial intelligence. So it's all about building things that are going to engage our young people, and you can do that now an awful lot quicker than you could before.
Talk easy here. So that
Sorry.
can you hear me now?
Yeah. Goodbye.
So the next question now we have is what lessons from math history are important for innovators today? Can you hear me now?
Yeah. I think a few stand out. First, breakthroughs often come from outsiders, and very often from play, from people following a question simply because it was interesting. And I think we've touched on this already to some extent. Sometimes the useless ideas, so-called useless ideas, have a habit of becoming essential decades or even centuries later. And so we should be wary of judging knowledge purely by its immediate payoff. So certainly in this day and age of almost immediate gratification, we have to be very careful about how we judge things. And then thirdly, despite the myth of the lone genius, real progress in mathematics is usually collaborative and cumulative, based on people building patiently on each other's work across generations and continents. And again, the story of Fermat, the proof of Fermat's last theorem by Andrew Wiles is a classic example of that, because his proof ran to over 100 pages of contemporary mathematics, but it all built on the ideas and the work that the others who tried to solve it contributed to the portfolio that he ultimately had to draw upon. And so often also the great mathematicians um, were often wrong quite a lot of the time before they understood that they were right. And so productive struggle isn't just a nice classroom value. It's literally how mathematics has advanced throughout the ages. And that's quite a liberating thing for, I think, a young innovator or a young learner to hear.
Thank you for that. So thank you for today. I really appreciate your time. So the last question we have here is: any advice for young professionals blending maths, AI, and innovation?
I think there's sort of four things really. Firstly is to learn the fundamentals deeply. Tools come and go, but foundations don't. And the people who understand the foundations are the ones who adapt fastest when the tools change. Secondly, I would say stay curious across boundaries, because the most interesting work now happens between disciplines and not necessarily inside them. This idea of interdisciplinary work is vitally important, because the problems that our world is facing now are highly interdisciplinary in nature. They're multifaceted, they're complex, and complex problems nearly always demand multifaceted solutions where you draw upon different areas of study and fields of study to help you solve a problem. So it's not about working in isolation any longer in any individual discipline. And treat AI as something to think with, not an oracle to outsource your thinking to. Your judgment is the most valuable thing that you have, and it's precisely the thing that AI cannot replace. And then genuinely be comfortable about being wrong, because as the history shows, that's often exactly where the learning takes place. So that would be how I would answer that.
With me, what can you tell people that math is all about? Math is beyond X, Y, solving for paper and paper. For the last one, so we can done for first episode for today.
Sorry, could you say that again, actually?
I said, what can you tell people that math is beyond X and Y, is beyond solving equation on paper, that math can do a lot of things for the modern world and innovation?
Well, I think mathematics is the thing that makes the invisible visible. It underpins so much of what we do today. So much of what we learn today, almost all of the technology has got some mathematics involved in it somewhere. As I mentioned earlier, you know, the logic gates and the chips that we use come from the Boolean algebra of the 1850s, the Bayes theorem, which is, you know, all about making predictions and working with probability, which is essentially what AI is all about. Large language models work on predicting what they think is going to be the next best thing, essentially. So it's a probability machine, and you go back to the almost the origins of probability theory, which were created through a conversation between Fermat and Pascal, a written conversation, because it was through correspondence, where they were trying to solve a problem, the problem of the unfinished game of dice or card game, whatever it was. And that laid down the foundations for probability. And without probability, we would have no AI. So, yeah, it's there, it's everywhere. You can't ignore it.
Yeah, I have. So thank you for today for the first episode of the Global Maths Blueprints broadcast. So thank you for having me, and thank you for accepting the invitation letter. Thank you so much. We're happy to have you today. So this is the end for the today episode. So we are moving to the next one. The next flyer, I'm going to do the next flyer very soon. Thank you so much. Thank you.
Thank you very much indeed for having me, Akinle, and I wish you all the best with your quest and maths with purpose.
Yes.
You're doing a great job. Thank you very much. Bye-bye now.
Bye-bye. Thank you.
Bye.